Now let's look at the Menec East alignments. So that was the west part. And now if we look at the east part, that's at the top there, looking on this photograph, coming down this way. So we'll zoom in on that. So here we have the lines of the Menec West. And then they come to this central part, which is a sort of mound where this house is. And then you can see they turn off there. You can see how the lines change direction. And at the end here, you can see the angle of the lines at the Menec East. You can see quite clearly that they're not aligned. But in the middle, it's rather quite complicated. If we follow the lines in the middle, we'll see that some of the lines towards the north fork off really towards the north and completely miss this part of the alignments. And then there are three other lines in the middle here, which are coming out in red now, which seem to converge to a point. But the major angle of the lines from the east come down like that, and you will see here that at this part of the alignment here, you actually have an alignment going along there. There's an alignment of stones actually follows that line, and you can see how the road follows that same angle. You see here it seems to have turned off and follows the same angle here at one point. So that's the projection of the Menec East lines here. But if we take the first row and project it further, we see that, in fact, the first row of the Menec East, if it's projected, actually links up to the first stone of the first row of the Menec West. And as we see, the most southerly line hits this line here and then stops where the road is. So let's have a look at the geometry of that. This is very interesting. If you follow this first line of the Menec East and link it up to the Menec West here, to the first row of the Menec West, then in fact it gives you the angle of a double square. You get a ratio of 1 to 2. So if you put two squares here, you actually link the Menec East to the Menec West by a double square. From the same stone, you see, from this same stone here, which we use to link up to Kermario for the triple square. So this is very, very precise. It's exact to 100th of a degree, which means that these people, this is 100th of a degree with respect to perfect north, south, and east, west. So which means that the builders had the capacity of perfectly calculating north, south, and east, west, and then tracing these angles at perfect directions, right? Which means you have to get rid of the idea of sort of early peasant farmers, you know? They didn't do that. This wasn't early peasant farmers doing this. This is very highly sophisticated and very, very precise engineering. So if we look at a general plan of that, I hope that's clear enough. I've traced that double square now by putting multiples. I've got 3 squares on the north-south side and 6 squares along the east-west line. 3 by 6 is a 1 to 2 relationship. But the advantage of having 3 by 6 is that gives me also the triple square here. The red line shows the angle of the Menec West lines, and the yellow line here shows the angle of the Menec East lines. So here I have Menec East 3 by 6, Menec West 2 by 6. Okay, or 1 to 3 or 2 to 3. And what I discovered after some years was that there's another geometry which fits into this. That already looks pretty astounding. But what I discovered, I did maths at university, and I was very fond of maths at school, and so I'm very fond of geometry in particular. And what I'm going to show you now, I never ever learnt about in school. What happens, in fact, is that you can trace a sevenfold square, which actually fits into this geometry. So these are 7 squares placed side by side. The side of this sevenfold square goes along the axis of the Menec West lines and along the triple square diagonal. And the diagonal of that sevenfold square goes along the axis of the East Menec lines and goes down the diagonal of the sevenfold square. Now this is exact geometry. You can express that in the following way. I don't know if you're into sort of trigonometry or whatever, but you can express that in the following way. If you take the inverse tangent of 1 over 3 and you add it to the inverse tangent of 1 over 7, that gives you the inverse tangent of 1 over 2. So this is a strict geometrical, arithmetical fact. What's quite astounding is that this was set up here about 7,000 years ago on a massive scale in Carnac. We can also express that by degrees if you prefer. The inverse tangent of 1 over 3 is 18.435 degrees. The sevenfold square has a diagonal angle of 8.13. If you add those together, you get 26.565, which is the exact angle of the diagonal of a double square. Okay? So this needs to be meditated on. But here's another picture of it. I actually discovered a stone. There's a stone here, which is exactly on that line. Perhaps there were other stones along here. A lot of the outlying stones were destroyed here in the 19th century. But there is one standing stone here, which is not in the lines and exactly here. And here, right in the corner, there's a standing stone just here. And in this part here, there is a remains of ruined stones, which were destroyed in 1905. We have traces of those stones being destroyed by people who were quarrying the stone in 1905. So the corner of this was actually marked, and there's still a remaining standing stone just there. So that's the picture with the double square in red, the sevenfold square in yellow, and the triple square in green. Okay, so that's the organization of these lines at Le Menec with a west side and an east side to them. Now we can extend this now to Kermario. We saw that this triple square goes all the way to Kermario, so which is the second part up here. Where am I? Up here, that's the Kermario lines. So we can now extend this triple square right to the dolmen, right? And from there, what I'm going to show you now is quite astounding. We can add on what I say is an extra. So we'll take the width of the alignments. Now, the Menec alignments are not exactly the same width as the Kermario alignments. The northern line moves slightly towards the north, as if the precise geometry had been done along the southern line, and that we'd slightly, because the width of these alignments is slightly larger, then there's a slightly different geometry going on here. And this is very interesting, because what we're going to discover is that from the dolmen to the northern side of the alignments here, we can add a module of 113 meters. It's exactly 112.93 meters. And that module, which I will call 1, right, it's 1 unit, will in fact show that the triple square has 4 by 12 of these units. So in other words, the width of the alignments, the north-south width of the alignments at Kermario here, is exactly 1/4 of the north-south distance between the dolmen and the first line of the Menec, and 1/12 of the east-west side. And what's very interesting is that this means that if you go from the first line of the Menec West line up to the most southerly line here of the Menec West, up to the most northerly line of Kermario, like we did here at the Menec to get our double square. Well, we went from the most southerly line to the most northerly line. Well, if we do the same thing here, we then have a ratio here of 1 + 4, 5, 5 to 12. That is a Pythagorean triangle, the 5, 12, 13 triangle. So what appears here now is another interesting geometry. Now, the angle of a 5, 12, 13 triangle is 22.62 degrees. So I'll show you that on Google Earth because you just really have to see it to believe it. So from north, that makes 67.38 degrees, okay? So if I come back to Google Earth here, and I put my pointer on the first stone again. There we go. And now I zoom out, and I come right up to the most northern line of the Kermario alignments, and I stop on this first stone here. There you go. Oh, missed it. 67.38. So it's the exact angle to 1/100th of a degree of a 5, 12, 13 triangle. Okay. So if you had any doubt before this that these people were doing geometry, there's no doubt now. I won't go into the measurements for the time being because we don't have time really. I've gone into that in detail in my book. Now what's interesting is if we had another module there, if I had another 113 meters north, and then I trace the line up here, of course that's going to give me 6 by 12, which is the double square, which means that this line goes right through the first line of the Menec East alignments. They go along that line. Okay, so these lines are traced along this side, okay? Now, of course, until Google Earth was invented for me, we couldn't know about this. I started working on these things with the maps, you know, these Ordnance Survey maps and rulers and protractors and stuff. And since we've had this material, it's possible to see, so this uses satellites and computers, and well, it's possible for us now to understand the exact precision that these people were using, right? Until about 10 years ago, we weren't capable of understanding what these people were doing. So this is, you know, hot news. So there's the double square. Coming back to Kermario then, and this summer solstice sunrise, we're now going to discover that all this geometry wasn't just done for sort of the pure pleasure of the mind. In fact, it's linked to the latitude. The latitude of Carnac has a specific property, which we'll look at now. Now, if we take from the dolmen now, we draw a line from that dolmen along the most southern row of stones, this line will lead us about 1 kilometer away to this very big stone here. It's called Lemanio 2 stone. It's on an earth mound, a low earth mound, which was constructed, and it's about 3 meters 50 tall, and that is visible from the beginning of the Kermario alignments, 1 kilometer away. And as you can see, it's much, much bigger than all the other stones around it. Now, the line going from the dolmen along the most southerly line of the Kermario alignments points to this. It goes through that stone like that. And that angle is 53.13 degrees from north. So what does this mean? So it's going from the dolmen here, along the southern line of stones, and right up here to this big Manio-2 giant at the end of the lines. So it's very, very precise. Now 15.13 degrees, what's that? It's a very interesting angle, in fact. See why? It's because it's the large angle of what's called a 3-4-5 triangle, the most famous Pythagorean triangle. And this corresponds to summer solstice sunrise here. So this is only true at this latitude. If you go further north, then your summer solstice sunrise will be further north. If you go further south, the summer solstice sunrise will be further south. Only at this latitude, and precisely at the moment that these stones were erected, we had the exact angle of a 3-4-5 triangle at this latitude at summer solstice. So the sun, it's not the sun's first ray, it's the center of the sun on the horizon. All right? So when the center of the sun is sitting on the horizon, then from the center of the sun, you have the exact angle of a 3-4-5 triangle. Now, the other angle of this 3-4-5 triangle, if we take it from east, the angle is 36.87 degrees. And one day I had another kind of revelation when I discovered that that angle is in fact twice the angle of a triple square. So that if you put a triple square like that with one diagonal on the east-west line at this latitude, then the other diagonal goes to summer solstice. This is also clear geometry. You can work this out. You calculate the angle of a triple square, you double it, and you get the angle of a 3-4-5 triangle. And it's not approximate, it is exact. To 100 decimal places, if you will. And as I say, so this is only true at this latitude. So we're beginning to understand where this triple square stuff comes from. The triple square is linked to the 3-4-5 triangle. And the 3-4-5 triangle was considered by the ancient Egyptians, we know, as the most perfect form in creation. So we begin to understand why these people, or these builders, came here to build this. Now, this led me to kind of formulate a rule to show how you can make any Pythagorean triangle from any two numbers. I got in contact with mathematicians from Sorbonne University in Paris and also from a professor in Berlin about this. And they said, well, it's never been formulated like that, but of course we could have known about it, which is an interesting way of putting things. What I'm going to show you now then, apparently, has never really been formulated like this as far as mathematics are concerned. So basically, we have a root triangle, what I call a root triangle, which has two values, A and B, which are any whole numbers, any whole positive numbers. And so in other words, if I take the triple square, then I have 1 here and 3 here. Okay? And the Pythagorean triangle, which will be, which comes from that, we obtain by these formula. So I multiply 2ab here, a squared minus b squared there, and a squared plus b squared there, and that gives me the Pythagorean triangle. And the angle is systematically doubled. So let's have an example here, the one we've seen with the triple square. B equals 1, A equals 3, so it's the triple square. So if I put those numbers in here, a squared minus b squared equals 8. a squared plus b squared, 9 plus 1 equals 10. 2a times b is 2 times 3, that's 6. That gives me a 6, 8, 10 triangle, which is 3, 4, 5. That's the same proportions multiplied by 2. 3, 4, 5 triangle. This works for any whole numbers. So you can find any Pythagoras triangle that you want from the two basic numbers. What I haven't pointed out, I call it the root triangle because the diagonal here is the square root of the value of this triangle. So the value here is the square root of 10. 1 squared plus 3 squared. That's 9 plus 1, 10. So the value of the diagonal is root 10, the square root of 10. And it gives you 10 here on the Pythagoras triangle. Okay? So I call it the root triangle. Now what I'm going to show you later is that the Egyptians used exactly the same thing here to situate the Giza plateau. Exactly the same principle. That's the angle, 18.435 degrees and 36.87 degrees. It's exactly the double. But before we go to Egypt, then let's just finish here in Carnac and see here how this works. So a 3, 4, 5 triangle can in fact be created using 2 triple squares. As you can see here, if I put 1 triple square horizontally like that, east-west, and then another triple square vertically beside it, that gives me 4 here and 3 here. And that's a 3, 4, 5 triangle. Okay? So this is this doubles the sort of triple square geometry. And what we see is that the angle here is doubled, as I explained. And so this line here, going along the most southerly line, and which gives this axis towards summer solstice sunrise, is exactly the double of the angle which comes from the Menec West. So let's have a look at that on a bigger scale. Here's the angle coming from the Menec West here. Here we are, from the Menec West to the Kermario dolmen. And then from that line, that's the line going from the Kermario dolmen along the most southern line up to the big stone here. I've sent it a bit further because there are actually stones in the woods here. And this field here was a site of the end of the alignments, which has been destroyed. And you can see around the edge of the field here, standing stones lying in the woods, which have been pushed out because when farmers wanted to farm, of course, then the stones were in the way a bit. And so quite a lot of destruction went on to make farming land after the French Revolution. So what you're seeing, you see, is that this line is actually doubled. The angle of the line is doubled from the east-west. So I have the triple square here, and the 3, 4, 5 here. And in the corner here is a tumulus called the tumulus of Kermario, and that's exactly in the angle of this 3, 4, 5 triangle. It's called the ancestor because it's one of the oldest monuments around. And it's untouched, very beautiful monument, the Kermario tumulus. So here we have then the whole scheme of things with the units involved, because what we can see is that these units, which we fixed 2 plus 4 plus 12, well, this double unit here is the basis of our 3, 4, 5 triangle. We're going to have 8 here, so that first triple square is 2 by 6, and then there's the other one, 2 from here, 2 by 6, and that gives us 6 by 8, and that's the structure, that's the measurement. So the whole thing is actually not only geometrical, but linked to certain measurements. And the line, the line going through the Menec East here, this double square line, goes through this point and up to this point. It's all linked.